You could be smart with calculus.
Calculus.
There is something called the moose calculus. As I recall, moose calculus was something somewhat complicated. All right, I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class and just ask you to guide our steps today. Help us to understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. All right, so last time I talked to you guys about how to find like tangent space and normal space to a given subspace of Euclidean space. I guess I'll give you another example of that. So just to get us started here. I guess I'll make it up. So example 1, we could have, let's say, use whatever letter you want. I'll use capital Phi for change. Phi of, let's say, ST, phi of ST is equal to S squared plus T squared and S and T and then ST. There we go. That's sufficiently weird. Although it seems like all my examples end up being 4-dimensional. Let's make it 5-dimensional. 47. There we go. So just to put it, 45 is not equal to 47, and well, like I told my other class, when and if the Department of Education actually is disassembled, we will party. We will have literal parties in my classes. Did that happen yet? I don't follow the news that closely. I'd seen rumblings. Okay. Yeah. Okay, so phi here is a mapping from R2 to R5. All right, and so this is a parameterization of a surface in 5 dimensions. All right, and let's see here. We could find. Let's try to find the tangent space and normal space at, let's say, phi of, I don't know, 1, 2. So that point would be what? 1, 2, I put it in there, I get what? I got myself a 5, 1, 2, 2, 47. All right. I'm going to call that point P because I don't want to keep writing it. All right? P. So I'm trying to find the tangent space at P and the normal space at P. The tangent space at P, TP, and let me give this more name calling here. Phi of R2, I'm going to call M. So M is a subset of R5. It's a surface. I just named it M. So I'm trying to find the tangent space at P to M. Now, if you, so in short, the way to do this is to take the span, basically simply of P, partial phi, partial S at the point P, and P then, no, I don't mean at P, I mean where? At plug in 1, 2. And this one will attach partial phi, partial T at the point 1, 2. That should do it for the tangent space. All I need to do is calculate the partial velocities to the map. Those will point in the tangential directions, and we'll be good. So let's work those out. So like partial phi, partial S, in this case is, we got here, I got a 2S, 1, 0, T, 0. Partial phi, partial T, I've got a 2T, 0, 1, S, 0. So I plug in 1, 2, what do I get? Let's see here, plug it in, what do we get? S equals to 1, t equals to 2, so I get 2, 1, 0, 2, 0. And what else? My other one, plug in, what would I have? T equals to 1, S equals to 1, t equals to 2, so that's a what? 4, 0, 1, 1, 0. All right, so there you go, those vectors span the tangent space to this surface in 5 dimensions. Yes?
What is M again?
M is a name for the surface.
Okay.
Yeah. If you'd like, we could call it Mom. Yes, let's call it Mom. Mom watches my videos, so she'll be honored. I got an aw. 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 That's her name. MC Cook. MC Cook. My brother-in-law fashioned himself to be a DJ once, but anyway. All right, so it's 2-dimensional. So if we're talking about a k-dimensional subspace of Euclidean space, we should expect that tangent space is likewise a k-dimensional set. Now, is this actually genuinely 2-dimensional? I think so, right? These are definitely linearly independent, all right? Okay, great. Now, how do we find the normal space? There's 2 ways. There's 2 ways to find the normal space. The one way, I'm not going to do it. The vector parts of the normal space at P to M can find from finding the null space of this matrix 2, 1, 0, 2, 0, 4, 0, 1, 1, 0. If we find the null space to that matrix, that gives us the vector parts, the vector directions needed for the normal. What's the dimension of the normal space? 3, right. So like for we always have this. We always have like all of the vectors based at P, we can write it as the tangent space to the surface we're looking at, or the manifold we're looking at, submanifold rather, and the normal space to the manifold. And we're only talking about manifolds which are explicitly subsets of Euclidean space at the moment, all right? So manifold is just a general word for a space with many directions. That's what manifold means, is many directions, right? If you read the King James, it talks about the manifold, this and that of God, right? It's like the many directional. Anyway, so this is a straightforward calculation. You can figure out the basis for the null space by a standard calculation of like linear algebra. And we did that last time a little bit. There's another way to go here, which is easier, which is if we can recast M as the solution set of a system of equations, then we can find the normal using the gradient method. That's easier. Let's see if we can do that. I just made up this example, so it might not be possible, but let's try. All right? So we're up against, so the question is, what variables do you want to use for R5? Cartesian variables. What should we use? Let me say we're going to work in R5. Let's call it X, Y, Z, W, and
J.
J?
I just do A through E.
J it is. All right. J it is. So here's the deal. Your mission, should you choose to accept it, is to take these equations. Do you remember that thing you did in Calculus 2 where you tried to take a parametric equation and find its Cartesian equation? Remember that? Well, that's what we're doing. But now with more letters. which makes it more fun. Now, obviously, there is, some of these are pretty easy. Apparently, j is equal to 47, right? So you got that. Done. Also, we got this one. Check, check. I guess. Wait, but do we have that though? That doesn't really do it, does it? So our goal is to solve for, well, let me put it in different words. We're trying to eliminate what? We want to eliminate S and T, right? Eliminate S and T. So, all right. So let me give you some guidelines here. We have the equation y equals to s. We have the equation z equals to t, but notice that s and t are both free. That means that if the system of equations, whatever we're looking for, there cannot be an equation that binds y or that binds z because they're free. So we're not looking for an equation, a standalone equation with those. But on the flip side, x is together here, right? So like, obviously we want to write down, I say obviously, but it's not obvious. We want to write x is equal to y squared plus z squared, right? Y squared plus z squared. That's good. Now we've got x without s and t. There's no way to fix these. These just reflect the reality that we're not binding y and z. W equals what? Yeah.
YZ.
All right. J was 47. Is that enough? How many independent equations should we have here? M is what? M is two-dimensional, right? We're starting in a five-dimensional context. How many equations do you need to fix a two-dimensional subspace? You need three. Those are our three equations. So we take those and we package them as a single mapping. I usually call it G. So you want G of like, X, Y, Z, W, J apparently. And that's going to be equal to, let's say, y squared plus z squared minus x, comma, yz minus a w, and j. I guess we could, I'll put the 47 in. It's kind of a, so here's the thing, guys. Like, you can always rearrange these equations so that your manifold in question is the inverse image of like 0. I've done that. You can always like take equations and put all the junk on one side and have it equals to 0. This is always an option. Now that we've done this, we can calculate the gradient. Nabla. So just to give you, so this is my G1, G2, G3, right? G1, G2, G3. Nabla. G1 is minus 1. Yowzers. 2y. Oh, I can't do math. I'm talking gradient. Let me write down what gradient means here before you guys are probably lost too. So gradient of a function in 5 variables here. Let me use little f for the sake of just arbitrariness. So we've got like partial xf, partial yf, partial zf, partial wf, partial jf, right? That's the gradient here. So I need to calculate that for my component functions, G1, G2, G3. All right, so like G1, the gradient is what? I was starting to write it down. Minus 1, 2y, 2z, and oh, there is no w dependence, there's no j dependence, so 0, 0. Great. Partial, the second component function here, take my gradient, I got, there's no x. The y differentiates to z. The z part differentiates to y. The w part differentiates to -1. There's no j dependence, so you got 0 there. And then the third component function, take my gradients, I got myself a 0, 0, 0, 0, and 1. So those vectors point in the normal directions at the point in question. So my normal space at the point P to M is the span of P comma something, P comma something else, P comma something else. And you guys help me out. What do I put in there? I need to plug in what P is, right? So I did these. These are the gradient to the level functions at arbitrary point x, y, z, w, j. But we're actually looking at the point 5, 1, 2, 2, 47, right? So I need to put x equals to 1, y equals to, oh my bad. Well, x equal to what?
X equals 5, y is 1, the next one's 2, the next one's 2, the next one's 47.
All right, so plug those in. We've got -1, 2, 2. Oh, my bad. What's 2 times 2? 4, 0, 0, 42. Hilarious.
Mod 2?
Don't you mod 2 me?
It's not even true. Or it is true. Full 0.
Don't try to confuse me. It's very possible. Let's see here. So 0, 2, 1, -1, 0. And, oh, the last one is easy to evaluate, right? All right, I feel better because like last time I kept doing 2-dimensional. Everything was 4-dimensional last time, you know? So here it's 5-dimensional. Yay! If we did this right, we should see that the tangent space to P is perpendicular to the normal space at P for this surface. For mom. Is it? Is the dot product of those vectors? And if it's not, I'm going to cry. So I'll write them over here again.
Perpendicular last one. The first one is also perpendicular.
We got what? 2, 1, 0, 2, 0, and also 4, 0, 1, 1, 0, right? If I take the dot product of this and that, I get -2 plus 2, a 0. Yay! Take the dot product of this and that, I get +2, -2, 0. Yay! Dot product of this and that, 0. The 4, 0, 1, 1, 0. If I take the dot product of this and the first one, I get -4, +4, 0. Yep, 0. Take dot product of this and that, I get 1, -1, 0. Yay! Take dot product of this and that, 0. Yes, indeed. These are all pairwise perpendicular. We actually managed to calculate this correctly today. Yay, thank you for your help. So, there you go. Now the other way to go here would be the linear algebra route of actually doing this computation, which in some sense is much safer, right? Because this business right here was creative, right? This is creative stuff here. This doesn't always work. You can't always take a parameterization for a surface and convert it to a system of equations. It may or may not be possible to actually do the algebra to make this happen. All right? Conversely, there are surfaces or higher dimensional manifolds defined as the solution set of equations which parameterizations of are not known. There are people whose whole career is actually based on finding a particular parameterization of some abstract manifold and like things that fall out of that. So finding a parameterization of an abstract space is an art form. But anyway, this is not that sophisticated, though. I just made it up, you know. So, all right. So there's that. Let's go on then. So next up, we want to talk about Lagrange multipliers. So the next story arc in here is the problem of constrained optimization. That's the problem we're dealing with here. The problem of constrained optimization. Let me set up the problem for us. We have some objective function, which I'll typically call f. All right? We'd like to make it as big or as small as we can. All right? But we're not just doing this in the wild. This objective function, to be clear, is a mapping from like Rn to R, all right? So this is n-dimensional optimization, all right? You've been taught methods of optimization in Calculus 1 for one variable, in Calculus 2 for still one variable. In Calculus 3, we do two variables, maybe three, right? And perhaps you saw the method of Lagrange multipliers in Calculus 3. You should have, right? It's a standard topic. We're going to bump that up a few levels in here. But next up, we have some constraint. But this time, it's going to be a constraint manifold. And it's going to be something like G of, x, let's say, equals to 0. And here G is a mapping, say, from Rn to Rk. So this is a what? This is an n minus k dimensional constraint manifold. Or you could say surface. If you don't like manifold, you could say space, all right? Just think of manifold as another word for space. Yep.
Any restriction between the size of n and k? Or does k have to be less than n?
Yeah, k has to be less than n. If k is equal to n, nothing's really left. Well, here, let's look at an example. Well, no example yet. First I must give you the general derivation. So we're trying to maximize this, right? So here's a totally somewhat abstract picture here. So let's call this constraint manifold M, all right? And M is equal to what? It's equal to the inverse image of 0. Because the thing I just did, I can always do. I can always set up my defining constraint equations as the inverse image of 0, right? A bunch of equations set equal to 0. Okay? And so this is some subset of Rn. And let's assume that there is a solution to this optimization problem at this point P, right? So suppose this right here, f of P extremal, right? It's either minimized or maximized there. Okay? You guys with me so far? Now, I have to assume that it exists. That's the starting point for the method of Lagrange multipliers. All right? That's also the place where Lagrange multipliers fails. I heard that.
I tried.
You can use the method of Lagrange multipliers, and you can solve the Lagrange multiplier equations, but if this initial assumption is not actually true, if there doesn't exist an extreme solution, then you're just finding things that may or may not actually be extremal. All right? So that is just the reality of the method. You have to be wary of the solutions actually being honest to goodness solutions. You have to double check your work when you're done. Yeah.
And that's a global or a local maximum?
I'm saying suppose it's a global extrema. Yeah. So if it's a global extrema, it's also a local extrema. So if we take any path, let's say gamma, right? If we take any path gamma which goes through that, what does it have to be the case? If I take G, right, and if I evaluate gamma of t, what should that be equal to? If this path is on the surface, manifold space, constraint space,
0.
that has to be 0, right? Because we're assuming it's on there. Great, but that has to also be true. And let's without loss of generality, we'll assume that this is where t is equal to 0, okay? We can always reparameterize the path such that t equal to 0 matches up with p. We're gonna suppose the gamma of 0 is equal to the point p that we're interested in, okay? For the sake of specificity. All right. So then what? If that's true for all t, and if the constraint, if the the level function there is differentiable, well, we can differentiate, right? We can differentiate. And so what does that give us? That gives us g prime of gamma of t times d gamma dt equal to d dt of what? 0, right? Which of course is 0. Now let me try to, I can write that, but let me break down what that means, what I'm writing, right? Because you're like, wait a minute, wait. Don't you mean Jacobian? Yes, I mean Jacobian, right? So this means the Jacobian of g at gamma of t times the, gamma prime of t. Well, I guess we should specifically say what? Okay, fine. This has to be equal to 0. Yeah, this is fine. Sorry, my mind was jumping ahead to a different part of the argument. Sorry. Okay, so that's true for all t, right? What does that mean? So this looks like what? This actually looks like what? The gradient to the first level, gradient, however many there are of these. Apparently there are k of them, right? That's a stack of gradients, right? Times gamma prime of t. What does this mean? Each one has to be 0, right? This means that the gradient to g sub j at gamma of t dotted with d gamma dt is equal to 0 for j equals to 1, 2, all the way out to k. This is very unsurprising if you stop and think about last lecture. What I'm saying is that the velocity vector to a path must be perpendicular to all of the normals to the constraint surface. The gradient of each constraint function is a normal to the constraint surface. Right? So this says that, gamma prime of t is an element of the normal space in gamma of t to the surface. Because this is, by definition, the tangent space at gamma of t perp. You'll forgive me, I'm suppressing. I'm being a little bit sloppy. Like I've added a p comma the vector before. Forgive me for violating my attach the p notation here to try to get the point across. Yeah.
If the gradient is normal and dotted with the derivative of gamma is 0, would that mean it's part of the tangent space rather than the normal space?
But the gradient to g is in the normal direction. About what we did last time.
So if it's perpendicular to the gradient, then it has to be in the tangent space.
Is that what I said? Oh, I'm sorry. Yes, my bad. Thank you. Yes. Anyway, I really said all this last time, but I'm just calculating again to emphasize the way it works, right? Here's the more interesting thing. P is the extremal point, right? So we can consider another function, right? Let's call it h of t. And that will be equal to the function, the objective function, composed with the path that's going through the extremal point, right? And this gives us a what? a function from the reals to the reals, right? This is a real valued function of a real variable. What has to happen at t equals to 0? It has to be what? Well, h of 0 is what? F of gamma of 0, which is? F of p, which is what? That's an extreme value, right? So if we look at values of the function that are close to t equal to 0 along the path, that has to be the maximum or the minimum for h along that path. Which is to say that if we calculate the derivative of this, dh dt, right, which is equal to the gradient of f at gamma of t, dotted with d gamma dt by the chain rule, well, that's just the arbitrary derivative. So if we look at h prime of 0, what is it, though? That's the gradient of f at gamma of 0, dotted with gamma prime of 0, right? Which tells us, in fact, that the gradient of f at p, right, has to be where? It's perpendicular to the tangential direction, right? Which means it's normal. Now, the thing that's a little bit slippery here, that you should see a gap in my logic right there. Because if you're perpendicular, okay, so I'll show you a second here. So this, I'm going to say that this implies, and I'm going to explain why in a second here, it's at the normal space at p to m, all right? But the reason for that implication is not supplied by just what I've written. Because if you think about it, could we have a vector which is perpendicular to another tangent vector? Like, is being perpendicular to one tangent vector enough to make it normal? No. Definitely not, right? But does this argument hold for just one path? No. This argument holds for every single possible path on the surface through that point. So as you cycle through all those possible paths, you cycle through all possible tangent vectors, which means that the gradient to the objective function has to be perpendicular to all possible tangential directions, which is to say that it's necessarily normal. All right? But now we can use, so this means then that the gradient of f at the point P, right, has to be in the normal space to the surface, the constraint surface at P. But that's equal to the span, right, of the gradient of the first objective function and the second objective function, and indeed the kth objective function at P, right? And what does that mean? That means that if we write the gradient of f, it should be equal to lambda 1 times gradient of g1 plus lambda 2 gradient of g2 plus plus lambda k gradient of gk. These equations must be solvable if it is indeed an extremal point. These are the Lagrange multiplier equations. So in Calculus 3, we usually just do one multiplier, because that's more than enough for most problems, right? But if you have a constraint, if you have a problem which is described by more than one equation of constraint, then you might have to use multiple multipliers. Now, if I try to make one of these off the top of my head, bad things are going to happen. Let me show you some examples. Let me use the projector here. You got to know your weaknesses. Making up Lagrange multiplier examples on the fly is not something I do. I don't get paid enough. Bad things will happen. I hope I've explained the method to you. And I hope you see why it's so important for us to understand the structure of the tangent space and the normal space. Because it's tight together here with this very applied problem, right? I don't have a lot of examples in those. I just got a couple, but we'll look at them. Come on. can find my laser. All right, so I just tried to derive this stuff for you guys. So here's the basic method is you choose n variables which describe your problem, you identify the objective function, write all the constraints as level surfaces. Anyway, so then you solve the gradient of f is equal to a linear combination of the gradient vectors to the constraint surfaces. Anyway, and then test the validity. Okay, so here's an example. You're like, well, you set up this really general thing, but all your examples are from Calculus 3. Yeah, fair enough, you got me. But anyway, so yeah, I'm sure the homework has something that's not Calculus 3, so that'll make up for it. I'll help you with it if you ask me about it. Anyway, so we wish to find the minimum and maximum distance to the origin for points on the curve x squared minus y squared equals to 1. All right? So first of all, before we even get into it, is there any hope? Is there any hope to find points which are, closest or furthest to the origin on the curve x squared minus y squared equal to 1? Well, I think there are closest points because x squared minus y squared equal to 1 is this hyperbola, right? So these are the points of closest approach, right? Is there a point which is furthest away from the origin on these hyperbolas? No. Certainly not, right? So, yeah. In any event, the objective function is the squared distance from the origin. That's easy to work with. And we have a single constraint function, x squared minus y squared. So I calculate the gradient of f, calculate the gradient of g. I seek solutions of lambda f equal to, a gradient of f equal to lambda g. That gives me 2x, 2y equals to lambda times 2x minus 2y, which gives me this equation and that equation. We have to solve these subject to the condition x squared minus y squared equals to 1. So first of all, notice that x equals 0 is not a solution because 0 minus y squared has no real solutions. But on the other hand, y equals to 0 works because x squared has solution, x squared minus 0 equal to 1 has solutions plus or minus 1. So that means that I can solve these with that. So I go here. Since x is not equal to 0, as we argued up here, I can divide, well anyway, I factor these. But I know that since x is not equal to 0, we must have lambda equals to 1, right? So I have lambda equals to 1. And since lambda is equal to 1, that forces y to be 0. So in short, hey, there you go. You like that? That's just for you, right there.
Right there, Violet.
Right there, Violet. That's yours. So 1, 0 and minus 1, 0 are the solution to the Lagrange multiplier problem. And you can see why that happened, right? The gradient to the constraint surface is like this, right? And the gradients to the constraint are like this, I think. Or maybe they're like that, I can't remember. But the gradients to the objective function, so here's some level curves of the objective function, right? The unit circle, radius 2 circle, and so forth, right? So the gradient to the objective function point radially outward. The two places where those gradients align are these 2 points. That's why the algebra led us there. However, as I warned you at the start, the method of Lagrange multipliers is not always successful. And here it's not really successful in total because there is no maximum distance from the origin, right? It did help us find the 2 points on the hyperbola which were closest to the origin, but we had to use common sense to check on that. How can we know that there is a solution to a constrained objective problem? What condition on the constraint surface or curve would be sufficient to guarantee that? Oh, here's pictures of the gradients. Yay! How about this? Here's a different one. Well, I'm going to leave that question there. We're going to come back to it. Here I wish to find the points on the unit circle which give extreme values for the function x squared minus y squared. I flipped the script. Now I've made the objective function of the last one the constraint function of the next one and vice versa. I just flipped the meaning, okay? So the algebra is pretty similar. Gradient of f equals to lambda gradient of g. And you work through the algebra. That's not really the point so much in here. And what you find is that there's 4 solutions, 0 plus or minus 1, and plus or minus 1, 0. These are the 4 solutions that respectively give objective function minus 1 or objective function 1. In fact, this is the honest-to-goodness global minimum of f on the unit circle. It's attained 2 places. And these are the honest-to-goodness global maximum of the objective function x squared minus y squared, which are obtained on the unit circle. What's the difference between the unit circle of this example and the hyperbola of the last example? They're very different constraints. Here's the difference. The hyperbola is not what we call compact. A compact subset of Rn is a set which is both closed and bounded. So it's closed in the sense of it doesn't have any fuzzy edges, all right? And it's bounded in the sense that you can put it inside a sufficiently large, like, open ball, right? So that's the case with the unit circle. It's got no fuzzy edge. See, a fuzzy edge could be a problem because if you have an objective function, it could be that the maximum for the objective function, it's where the edge fuzzifies. And so then you never actually get there, but that might be the maximum that you need. But if there is no fuzzy edge, then the maximum actually has to be obtained. The minimum also has to be obtained. This theorem I'm quoting has a name. It's called the extreme value theorem, and it states that for a continuous function with a compact domain, it attains its minimum and maximum. This is called the extreme value theorem. You see it in Calculus 1 as the closed set test. If we have a continuous function from, that takes, if you're looking for the maximum on like a closed set from A to B, we know that we find a minimum and a maximum on that set, and we can find it by checking f of A, f of B, and looking for any extremal points in between, right? So the generalization of that is called the extreme value theorem. And I use this word compact, like I said, closed and bounded. That has a more technical topological definition. This is a much more general theorem than advanced calculus. It's really a theorem of topology. But anyway. So here's what happened. This is a picture. This is the constraint curve. Here are some level curves of the objective function. And as you can see, the places where we maximize are exactly where the gradients of the constraint curve and the level functions aligned. And solving the Lagrange multiplier equations finds those points for us. So. All right. See if I have any others. I think this is one that doesn't work. Sometimes it's helpful to have examples that don't work. So here I have the constraint equation xy equals to 1. This is not compact because what that is the graph y equals x, y equals 1 over x, which by the way it's a hyperbola rotated 45 degrees. So the constraint is actually a hyperbola. That's very, very much not compact. It's closed, that's true. The complement of the red curves is the whole plane with a fuzzified this cut out. And if you look at that, every point's interior. So the red curve is a closed subset of the plane. However, it's not a bounded subset because I can't contain the hyperbola in any finite ball. It just goes on and on. Okay, now here my objective function was x. I chose x. So the level functions to the objective function are just these vertical lines, right? These are curves of constant x. And if you try to solve the Lagrange multiplier equation, do we get anything? Did I even get a solution? Lambda equals to 0. If I put that, then I can't solve the 1 equals lambda y equation. So I must have x equals to 0 for the Lagrange multiplier equation. But if x equals to 0, then y equals to 1 is not solvable. So we find no solutions. So this is an example of, it's kind of an interesting example in some sense. In other sense, I should just cut it out of my notes because it's wasting my time. But maybe it's a useful tale because what it shows us is sometimes we can set up the Lagrange multiplier equations, find no solutions, and that's just as well because there is no solution to the given problem. Because if you think about this, is there any x, like I'm asking the question that we're trying to maximize x subject to the, xy equals to 1. Is that possible? No, I mean, of course not. Like, this goes on and on and on and on and on forever, right? X gets arbitrarily large. So there is no maximization of the objective function x. And likewise, there's no minimum because it keeps going that way too. So yeah.
Does that demonstrate that the constraint is not compact
That constraint is not compact. That's true.
because of the calculation?
I don't think that is the case, no. Because of the calculation. That I'd have to think more on. That's an interesting question. Does inability to solve, if you can prove there are no solutions to the Lagrange multiplier problem, does that prove that your set is not compact? I mean, you need additional qualifying because certainly we can talk about subsets of the plane which escape calculus, right? If we've got corners and cusps and stuff, we can't capture those kinds of subsets of the plane using like a level set, right? Level sets are necessarily like smooth data. If we have jagged data, it's outside our purview, Let's see, how about this one? Here I have f of xy equals to x constrained to, this is the hyperbola again, and so I get a maximum at 1, 0, and I get a minimum for the Lagrange multiplier equations of -1 at -1, 0. But both the alleged maximum and the alleged minimum are both illusory because, of course, the objective function x gets as big as you like and as small as you like relative to the hyperbola, which opens sideways like this, right? So we've just found fake solutions that are at the vertices of the hyperbola here. So these are not genuine solutions, despite the fact that we found, we solved the Lagrange multiplier problem, but these are not honest-to-goodness solutions to the extreme value problem here. So anyway, all right. I think that may be all I have in the notes here. That's a picture of what just happened. So like here's the level functions for x. This is the constraint, the non-compact constraint curve, right? And these were solutions, but they're not actually maximums or minimums for x, right? Okay. Yeah, shout out to Edward Frankel at Berkeley. His lectures on this stuff are just amazing. This is a very interesting mathematician. His autobiography, I think, is Love and Math, and it's one of the better math books I've ever read. That's just about his life and growing up in Soviet Russia and escaping that, sort of at the tail end of the Cold War, and the persecution he faced as a secular Jewish person there. And it's very, very interesting autobiography. I highly recommend. Don't read the last chapter. You have to stop before you get there. I'll just say that. It is not Liberty approved. I'll just say that. Now you're all just going to find the book to read just the last chapter, of course, but he's very interested in this. What's that? What?
She said, well, that's good. And I said, no, I don't think so.
No, I mean, so so
Yes.
there's this like silent Japanese film where this guy writes a poem on the back of some woman with no clothes, and I think it's like the same thing, but like with an equation. It's a short film. It won award stuff, but it does have nudity, and you just don't want to see it. Trust me. Just don't see it. Don't see it. It is very artistic. It is very, very very artistic. But and I'm sure the equation was very beautiful. But no, I don't think I need to edit anything. I'm warning you that that's what's the last chapter in the book. And if it wasn't for that last chapter, I would make it required reading for Math 450 if I was teaching it. Because otherwise, the book is an incredible testament to just the fact that mathematics is part of God's general revelation, which even a secular Jew can recognize as being transcended above the human experience. That, he saw in math that man is more than a machine, that there's something beyond just the here and now. That's what he saw in math. Because of the unanswerable questions in math, the unexplained connections in the things he was studying. So he's a brilliant mathematician, probably one of the maybe best 10 alive right now. Way beyond me. Okay, so I'm sorry I don't have a more nefarious example to show you right now, but I think if I can find a good fancy schmancy multiple Lagrange multiplier problem to show you next time, I'll do that. I ran short on preparation. Oh, thanks. Preparation. Wait a minute. Yeah, that's what I thought. I ran short on preparation time this week, so I don't have that. But what I should show you is I should just get into the next thing. That's probably what's best for us. So let me do that. All right, so Lagrange multipliers, fantastic method to solve constrained problems. All right. And like I said, I owe you a more abstract example, and I will try to find at least one, maybe two, maybe even three more abstract examples for you, past Calc 3 style, all right?
This won't work with inequalities. This won't work with inequalities, right?
Inequalities are inappropriate here because, well, inequalities inevitably involve jagged things, right? If I have so you guys remember the problem of linear programming from college algebra perhaps? You have a function of two variables, you've got a system of inequalities, you graph those inequalities in the plane, right? Any maximums or minimums of that linear objective function have to appear at corners, right? That is outside our purview. And the higher dimensional versions of that are also outside our scope because, parallel, what are those things called? What's that? Parallelepipeds. Things that have corners, we can't capture with equations that are smooth. Smooth equations aren't going to have corners for the most part. I mean, you might have a cone, but some of those things are just better described with inequalities. And so, in some sense, part of that's a little bit outside my scope in here. If you really want to solve those kinds of constrained optimization problems, you probably need to study the simplex method, which is the province of operations research. But the general theory that we're going over in here will motivate some of their methods as well. So I wouldn't say that these are disconnected questions necessarily. But the question you're asking is a good one because it brings us to the next question, which is, so I've just told you how to find maximums on smooth data, right? We Lagrange multiplier problem. But what about finding local maximums? How do we do that? What's the story of local maximums? So that's the next question is what about local extrema? Right? So given a function, let's say from Rn to R, when is f of p, a local min-max? So maybe you already kind of know part of the answer to this is what? What should we have at such a point? Yeah?
Zero tangentness.
Zero tangentness.
We should have all the directional derivatives be zero.
We should have all the directional derivatives be zero. That seems very reasonable, right? Because if it's a local extrema, right, that means that if we're close to it, we're neither increasing nor decreasing away from the point, right? So it must be yes. It must be that all the directional derivatives are zero. How can we get that all the directional derivatives are zero? How about this? If we know all the partial derivatives of the function are zero, that would give us a local max min, possibly, maybe not. But if it is, it should have that, right? What I'm saying is, if it is a local extrema and the function's differentiable, yes, all the partial derivatives must be zero, right? However, you should remember from your Calculus 1 experience that just because the derivative is 0 doesn't mean it's a local max or min, right? We could have derivative 0 and it could be like x cubed, right? The x cubed thing. But yes, so first of all, definition, P is a critical point if the gradient of f at P is equal to 0, or if the gradient of f at P is undefined, right? So we up our game from critical number to critical point, yeah? And then, check this out. There is a theorem given sufficiently nice function, f. I'm going to ignore that, Rn to R. Although it does beg the question, after I said that I'm going to ignore it, did I really ignore it? Is it possible to make a comment about ignoring something? I guess I could ask you a question. Here's a question I always ask people. So like, I'll ask you, Sam, is there anyone that you don't know? Name them.
Ben Stewart.
Michelle Obama.
Then you know him.
No, I don't.
Oh,
No.
dang it! You were prepared for this. Son of a gun. It usually works. I need to find dumber students. All right.
I bet you I don't know Jackson.
So here's the deal. F of x is equal to f of p plus the gradient of f at p times x minus p dot x minus p plus the quadratic form at p based at x minus p plus higher order things. Now I have a better formula for this, but I'm just going to write it this way to start with. Now let me kind of expand on what this is here. This in formula is more like this. I could do x minus p transpose times a matrix, which looks like the following. fxx at p. I can't use x1. x1, x1, f x1, x2. I don't like that notation. This notation's hideous. Let me do better. Sorry, guys. Partial squared x1 at f. Partial x1, partial x2 of f. I'm going to drop the, I'm not going to write the of p in here, okay? This is all at p, all right? Partial x2, partial x1 of f, partial x2 squared of f. All right. This goes on. Eventually you've got partial x1, partial xn of f. Next one down, you've got partial x2, partial xn of f. And this goes on. Down here you've got partial n squared of f. I've got a better way to write this, but I'm just writing it out in detail like this for just a second here. Like that. So this is all at p. This is what's called a quadratic form. So this is like the quadratic form at p. Maybe I should put a sub p. I don't know. I can't decide the notation. I'm sorry, guys. So this quadratic form acting on x minus p is give me that. It's a better way to write it.